Greetings, everybody. This video covers it's the first lecture for Chapter 4. The next unit will cover Chapters 4, 5, and 6 in the OpenStax text. And so this is the first one from Chapter 4. And all three chapters deal with Newton's laws. Okay? Well, I think you all know that there are three Newton's laws. And we refer to them as Newton's first law, which is also called the law of inertia. Newton's second law is the most important one that we'll focus on for the next test. And then we also have Newton's third law, which is also called the law of action-reaction. So let's just get a couple of background terms out of the way. Well, as you probably know, and if you don't, that's fine, but Newton's laws deal with the force acting on an object, the mass of an object, and the acceleration of an object. And so what is a force? Well, simply put, a force is simply a push or a pull. It is an interaction between two objects. And sometimes they're called the two objects. One is called the agent and the other is called the object. But I'm not real big on that. Basically, a force is a push or pull that that occurs as a result of an interaction between two objects. But here you can see the agent is the object that does the pushing or the pulling. So in this picture, the woman is the agent and the car is the object. In other words, she's the one pushing the car. But yeah, so that's just something to know. Now, Newton's first, let's take them in order. Newton's first law is the law of inertia. And basically, Newton's first law can be stated a couple of different ways. Well, let's consider an object that has no net forces acting on it. Well, if it's at rest, it's going to remain at rest. And if it's moving, it's going to continue to move in a straight line and at a constant speed. The key is that the object has no net forces acting on it. So if the object's at rest, it will remain at rest. And if it's moving, it will continue to move in a straight line and at a constant speed. And it will continue to, in either case, it will continue to do that forever and ever, unless a net or external force is finally exerted on it. If you have an object resting on a table, it's not going to move unless you pick it up or unless you knock it off the table or anything like that. Well, what is inertia? Well, inertia is important because we're going to relate it to mass. Well, the physics definition is that inertia is the tendency of an object to resist or oppose changes in its motion. That might seem like a little bit of a handful. Well, let's consider, I like to consider the following two cases. Case one, your neighbor leaves two objects parked in your backyard, a skateboard and a heavy dump truck. Why, who knows, but just, so the neighbor leaves a skateboard and a heavy dump truck parked in your backyard, so they're not moving. Now, you get up in the morning, you're going to need to move each object so you can drive to work. And say, well, which one is easier for you to move? Well, you'd say, Dr. Gomez, the skateboard, obviously. It has a much smaller mass than the truck. You can just easily push it aside. To move the heavy dump truck, assuming you don't have the keys, you'd have to have it towed. Well, we say in the language of physics, we say that the skateboard has less inertia. Obviously, you say, well, yeah, Dr. Gomez, it's much, much, much smaller than this huge dump truck. But in the language of physics, we say that the skateboard has less inertia. So it is easier, because it has less inertia, it's much easier to change its motion. The truck has a much larger inertia relative to the skateboard. It's much more difficult to change the motion of the truck. Well, let's consider the second case. Suppose you have a teenager on a skateboard. And he's on his headphones, he's on his iPad, he's maybe not paying attention, and he's gliding very slowly toward you on the sidewalk. Not going very fast, but he's not paying attention. He's gliding toward you very slowly. And later that same day, maybe it's just not your day, the heavy dump truck, somehow its parking brake gets released, and it starts moving towards you at the same slow speed as the skateboarder. And I say, okay, which one is easier for you to stop? Well, the skateboard, obviously. You can easily step in front of the kid on the skateboard, and you can put your arms out and stop him. You say, whoa, kid, hey, pay attention. But physically, you would not be able to stop the moving truck. You'd have to get out of the way. Again, in each case, we say that the skateboard has a much smaller mass than the truck, so it is much easier to stop. Well, again, in the language of physics, we say the skateboard has less inertia. Again, it's much easier to change its motion. It doesn't matter. That change in motion could be something is at rest, you want to get it to move. Think of the first example. The truck and the skateboard are both parked in your backyard or in your driveway. You need to move them so you can go to work. It's much easier to move the skateboard than it is the large truck. Likewise, the second case, if each one is rolling towards you at a very slow speed, you can stop the kid on the skateboard, but you sure as heck cannot stop the big truck. And then you're saying, you're thinking, well, Dr. Gomez, it's pretty obvious. The truck is probably 100 times more massive than a skateboarder. So naturally, it's a lot easier to move the skateboard if it's parked, or stop it if it's moving. And of course, you're correct. And the key is the mass. The truck has 100 times more mass than a skateboarder, so naturally, it's easier to move the skateboard. Skateboard. Left out that word, skateboard. Yeah. And again, misspelled it. And yeah, and it's correct. In other words, it's more difficult to change. It's more difficult to change the motion of the larger mass because it has more inertia. So mass is the quantitative measure of inertia. The larger or smaller the mass, the more or less inertia it has. And we use the lowercase m to indicate mass. And in MKS units, mass is measured in kilograms. Meters, kilograms, second. Okay, so that's the law of inertia. Now, what is Newton's second law? Well, Newton's second law, what it does is it provides a mathematical relationship between the force F acting on an object, the mass m of the object, and the acceleration a of the object. Newton's second law is actually a vector equation. It's very important. It's actually a vector equation. But before we actually get into the mathematics of Newton's second law, again, it's a vector equation. You have to treat x and y separately, etc., etc. But before we even worry about that, let's look at the vector nature of some basic or some fundamental forces. Well, again, force is a vector. The general symbol for the force is the vector symbol. Just F here with the arrow on top. Any vector you draw it with the arrow on top. Nothing complicated. Here's an example. You're hitting the cue ball with the cue stick, and the cue stick is the agent. It exerts this force, indicated by the red vector. It exerts a force on the cue ball. But again, I'm not really big about agent and object. Basically, pretty obvious. One object is exerting a force on another object. In this case, the cue stick is exerting a force on the cue ball. In the previous example, the woman was pushing her car. Well, the MKS unit of force is a Newton. 1 Newton is equal to 1 kilogram meter per second squared. There's forces known as contact forces. They're forces that act on an object, but the objects have to be touching. The agent has to be touching the object. One object has to be touching another. Contact, they're in contact. We'll find out in a few minutes the normal force, Fn. And for normal, F for force. The normal force, Fn, is the contact force. Long-range forces are forces that act, as you could probably guess, without physical contact. The the force due to gravity is a long-range force. For example, if this coffee mug gets dropped, you might drop it, it might get knocked off a shelf or off a table. Well, gravity, the Earth's gravity is pulling the mug in the negative y direction, but the mug is not in contact with the Earth's surface, right? It falls. If you're outside, it's going to fall to the ground. If you're inside, it's going to fall to the floor. But it falls. It doesn't have to actually be touching the surface of the Earth for that force to be acting. So mg is a long-range force. Well, and we'll find out later what is weight. Weight is the object's mass times g, which is acceleration due to gravity. We're going to look at in these next 3 chapters. We're going to look at what I call 4 of the most common forces. And remember, force is a vector. All right? So these forces have a specific magnitude and a specific direction. Well, what we're going to focus on first, before we worry about the math, what we're going to focus on first is these 4 most common forces. How do we draw them correctly? Why? Because if we can't draw them correctly, how will you be able to apply Newton's second law? It's a vector sum. It's a vector equation. And if you can't draw these vectors correctly, how do you get them into their x and y components? So we're going to look at, before we worry about Newton's second law, we're going to look at how to draw what I call the 4 most common forces. And I'll do 2 in this lecture and 2 in the next one. And again, these aren't the only 4 forces that occur in nature, but for what we'll see in the next 3 chapters, these are the 4 most common. And I'll do 2 in this lecture and 2 in the next. Well, first one I call weight. Well, I don't call it weight. It is weight. It's the weight force. And what is weight? Weight is the force on an object due to the Earth's gravity. We use an uppercase W for weight. It's a vector. And weight is simply equal to mg. Well, remember, g is a vector. G is an acceleration. Force and acceleration are vectors. So you have W vector equals, and remember, mass is a scalar. M is a scalar. Mass has no direction associated with it. So W equals mg. Now notice W always, 100% of the time, points in the negative y direction, because that is the direction of the Earth's, the acceleration due to gravity is in the negative y direction. So if W equals mg, W darn well better be in the negative y direction. And so how do we, remember, all we're concerned with in these first 2 lectures, how do we draw these forces correctly? Well, how do we draw, and again, every object in the Earth's atmosphere will experience a weight force. It doesn't matter if you're in Tifton, Georgia, Boston, Massachusetts, Calcutta, India. Every object in the Earth's atmosphere will experience the weight force. What is weight? Mass times gravity. What is gravity? 9.80 meters per second squared. What is the direction of the weight force? Negative y 100% of the time. So let's look at a couple of these examples. Here's a person. They could be standing outside on the ground, on the flat ground. They could be standing on the floor of a room or a warehouse, or they could be standing on the roof of a building. We don't care. But they're on a horizontal surface. Well, every object in the Earth's atmosphere experiences a weight force. Weight is always directed, it's always in the negative y direction. I've taken great care when I draw that vector that I'm not drawing it, I'm not drawing it like this, or at some random angle. It's always a, notice that vector, and you label it mg, because what is weight? Mg. Straight down, negative y direction. Okay, what if this person, instead of being on a horizontal surface, what if they're on a ramp or an incline? Well, it doesn't matter. A person could be skiing, could be going down a water slide, who knows? But it doesn't matter. He's on this incline. Well, an object in the Earth's atmosphere, weight is mg. Notice, even though he's on the incline, I'm taking great care. That vector, that green arrow representing the mg, clearly it's pointing straight down. Again, it's not complicated, but we don't want to get careless. I'm not drawing it like over this way, or I'm not drawing it you know, you know, over like that, any random way. It's always weight is always straight down. Okay, now let's look at this third panel. It's a projectile motion picture. Someone is shooting this basketball. It's undergoing projectile motion. Well, remember, in projectile motion, the acceleration is always negative g, i.e. in the negative y direction. Well, no matter where this object is on this trajectory, the weight is always pulling in the negative y direction. Even, you see, it's rolling at rest, undergoing projectile motion. Doesn't matter, because any object in the Earth's atmosphere, you don't turn gravity on and off, so you wouldn't turn the weight force on and off. So again, what is W? mg, always. What's the direction? Negative y. See that? And you get the idea. Let's look at one more. This is the ubiquitous bug on the bowling ball. This is a perfectly spherical bowling ball. This bug is crawling up towards the north pole of the ball. Well, any object in the Earth's atmosphere, be it a bug or a bus or, a car, a person, experience the weight. mg, notice I've taken great care. mg is clearly drawn exactly in the negative y direction. All right, you can see, just look at those examples. Weight is always in the negative y direction. What is weight? mg. M is the object's mass in kilograms. G is the acceleration due to gravity, 9.80 meters per second squared. So that's how to draw the weight force. Again, remember, right now, we just want to, and again, over here, what's the weight force on the bug? Notice that vector clearly points in the negative y direction. We don't want to get careless. All right, well, what's the second force we're going to look at today? Or not today, in this lecture, in lecture 1 of chapter 4. Well, the normal force. Normal force, and I write it with an uppercase F and then a capital N subscript, so Fn for the normal force. And you have a normal force whenever an object is in contact with a surface. So an object has to be physically touching a surface. The normal force is a pushing force. It is the force of the surface pushing on the object. Now, the word normal in this case doesn't mean normal in the psychological sense of the word. It means normal in the physics and mathematical definition, meaning perpendicular. Normal means perpendicular. Fn is always perpendicular to the surface. Whatever surface that the object is in contact with, the normal force will always be perpendicular to the plane of that surface. Now, in this case, the direction of Fn, it depends upon the geometry of the object and the surface that it is in contact with. And we'll see some different cases. But the key is normal means perpendicular. Perpendicular to what? Perpendicular to the surface. By that we mean it's understood the surface that the object is touching, the surface that the object is in contact with. Again, how do we draw Fn? Well, unlike mg only has one direction, negative y. The normal force, again, depends on the geometry of the object and the surface. What do they look like? Okay, and I've also gone ahead and in each case, I've drawn mg again. We can't, there's never too much repetition in terms of drawing these forces. Well, in case 1, we have, again, this person. He's standing on a horizontal surface. Well, there's the weight force, mg, notice clearly straight in the negative y direction. Now remember, an object, in this case the person, in contact with a surface, in this case, he's in contact with the horizontal surface. Again, it could be the ground, could be the roof of a building, could be the floor of a warehouse or some room. Doesn't matter. Object is the person in contact with a surface. Normal force. Normal to what? Normal to the surface. So see this vector Fn that I've drawn representing the normal force. And again, what is Fn? You always draw it. You draw it from the surface, and you draw it. It goes through the object and ends up pointing away from the surface, and also away from the object. And notice if we were to zoom in on that first diagram, you'll clearly see again that green vector that I've drawn representing Fn, I've extended down. Clearly, it makes a 90-degree angle with the horizontal surface. And it's again, it's the pushing force. You draw that vector from the surface, draw it through the object, pointing away from each. Now let's look here. Let's look at the second example. Again, the person on the incline. And notice, again, the MG, I've drawn MG because, again, it's a good habit to get into, to draw all the forces that we understand. Well, again, MG clearly in the negative y direction. Now notice the surface in this case is the incline, the ramp, the hill. Well, object in contact with a surface, Fn. Again, Fn points from the object through, from the surface, it points from the surface through the object, and it's pointing away from each. And notice again, this green vector I've drawn, it's clearly makes a 90-degree angle with respect to that surface. Again, and we draw again from the surface through the object, it's pointing away from both of them. But clearly that vector has to make a 90-degree angle, has to be perpendicular with the surface. And let's look at the bug and the bowling ball. He's over here. Well, notice this blue dotted line, that's the tangent line to the surface of the bowling ball, right where the bug is located, right where the bug is in contact with the bowling ball. That blue dotted line, that's the tangent. Well, again, bug is the object in contact with the surface. He's sitting on the surface of this bowling ball. Normal force. And again, it's the pushing force. It's the force of the surface of the bowling ball pushing on the bug. It's always from the surface through the object, and that arrow has to point away from each. And notice that green vector I've drawn representing Fn, it clearly is making an angle of 90 degrees with that tangent line. So, oops, I don't know what I did there. Pardon me. Let me go back. Yeah, so, and again, just to emphasize, I've drawn the weight in each case. The weight is always equal to mg, but important with normal force. Normal means perpendicular. Perpendicular to what? To the surface, and it's the pushing force. It's the force of the surface pushing on the object. All right, so that's how to draw W and mg. Excuse me, W is mg. That's how to draw the normal force Fn and the weight mg. And notice there's three good indications. Notice mg, the direction never changes. Negative y, negative y, negative y. But Fn depends on the geometry of the surface. Fn is in the positive y direction in this first case. Fn here, it's perpendicular to the incline in this second case. And in the third case, Fn is perpendicular to the tangent right at that point where the bug is in contact with the bowling ball. Alrighty, so I'm going to save this video and then post the next one. Okay, I want to try to keep these fairly short to, limit shorten the download time.